Welcome back. With this video, we're gonna open our new chapter, chapter 10, and we're gonna focus on law of sines in this first section. So far, we we focused on the right triangles. I will remind you that a right triangle is a triangle in which one angle is a 90-degree angle. But we know right triangles don't cover all of the situations that come up. So we need to learn how to work with other triangles. So the triangles that do not have a 90-degree angle are called oblique triangles. And that's what we're going to focus on in this chapter. So in this section, we will use the law of sines to solve oblique triangles. We're going to find the area of an oblique triangle using sine function and solve applied problems using the law of sines. So focusing on the law of sines. Here's an example where oblique triangles are involved, and this is a real situation. We have a plane that's in motion, and then we have two stations 20 miles apart that with radars that actually communicate with the plane. And we know that from the first radar, the plane forms a 15 degrees with the ground, and from the second station, the plane forms 35 degrees with the ground. Could we tell the altitude of the plane? So if we're just, as we can tell, none of the angles form 90 degrees here. So we have 15 degrees, 35, that's 50 in total. So that means that this angle is 130. So none of this triangle is not a right triangle. So we cannot apply our regular sine and cosine or right triangle geometry here. Well, one way to go around it is to put a perpendicular line to the ground here from one of the vertices, and then look at one right triangle and another right triangle. That's the way of going around it. But we want to be able to work with oblique triangles directly without forming two right triangles. And the law of sines will help us in that. So as we already mentioned, any triangle that is not a right triangle is an oblique triangle, and solving an oblique triangle means finding the measurements of all three angles and all three sides. And to do so, we need to start with at least 3 of these values, including at least one of the sides. We will investigate 3 possible oblique triangle problem situations. So let's focus right now. We need at least 3 values from our triangle, and out of those 3 values, we need at least one side. Okay, so here are our possibilities. First, we know a side and 2 angles, and the side is enclosed between those angles. Now that will be a situation number 1. It's called angle side angle, ASA for short, right here. And then situation number 2, AAS, that refers to angle, and the side. So notice that in this situation, the side is not included between the angles. It's actually on the side of one of the angles. This situation is described as, abbreviated as AAS, angle, side. And situation number 3, we have 2 sides and an angle, where the angle is not in between those two sides. It's on, on the outside of one of the sides. And this situation is described as side-side angle, or SSA for short. Knowing how to approach each of these situations enables us to solve oblique triangles without having to drop a perpendicular to form two right triangles, like we mentioned before. And instead, we can use the fact that the ratio of the measurement of one of the angles to the length of its opposite side will be equal to the other two ratios of angle measurement to the opposite side. Now, let's look at it in the formula. The same statement written down. So here we are. We said the ratio of sine of alpha divided by side A is the same as sine of beta divided by side B is the same as sine of gamma divided by side C. Or we could flip these ratios and say that side A divided by sine alpha is the same as side B divided by sine beta is the same as side C divided by sine gamma. Now, notice how the sides and the angles of the triangle are labeled. That's important. So side A is always across from angle alpha. Side B is always across from angle beta. And side C is always across from angle gamma. So only then these ratios work if we label our angles and sides in this matter. All right, so now let's actually go ahead and see how these ratios came about. How did we come up with those ratios? Let's take a look at an oblique triangle, which is labeled the way that we just described, right? So we're gonna actually put a vertical line from angle gamma onto the side C. And it's a perpendicular line, so we're looking at the two right triangles here. So we could apply our functions of sine alpha and sine beta. So let's write them down. So sine alpha is going to be the opposite side over hypotenuse. So that's going to be h divided by b. For sine beta, we're going to have opposite, which is also h, and we're going to divide by the hypotenuse, which is a. Okay, so now let's solve each of these equations for h. So in order to solve this equation, we're going to multiply both sides by b. And in order to solve this equation, we're going to multiply both sides by a. Okay, so what do we have? We have b times sine alpha equals h, and also we have a times sine beta equals h. And since they both equal the same thing, they both equal h, then they must be equal, right? Because h equals h. So from here, we can conclude that b sine alpha equals a sine beta, right? But okay, I'm gonna copy this statement. B sine alpha equals a sine beta. And now I'm gonna divide both sides by a times b. Okay, so B and B, the common factor will cancel out, and we could do the same thing on the other side, cancel out A. What do we have? We have sine alpha divided by A equals sine beta divided by B. And also, we could prove in the same way, same exact manner, that sine alpha over A equals to sine gamma over C. And so it's already equal to sine beta over B. We have our law of sines formula. Now I want to do it again. This time I'm going to divide by sines. So we had B sine alpha equals A sine beta. But this time, instead of dividing out A and B, I'm going to divide out sine alpha multiplied by sine beta. All right, so we're gonna again cancel out the common factors. And what do we have? We have B divided by sine beta equals A divided by sine alpha. And again, we could, in the same way, we could derive that A divided by sine alpha also equals C divided by sine gamma. All right, so yeah, this is also the same. It's the same law, only our ratios are flipped, so it works both ways. So that's our derivation of the formula.